Okay, hello everyone, and welcome to this June 2026 edition of the Rocky Worlds Discussions, where we're very excited to be hosting Eleonora Alei from NASA Goddard, who's going to talk to us about not one, but two future space missions. But before we dive into the talk, I'm just going to remind everyone of how we run things here at Rocky Worlds. The schedule is that we'll have an uninterrupted talk for the first 30 to 40 minutes or so please do keep yourselves muted. And then after that, we open up the floor to discussion where you can raise your hand and we'll call you forward. Hopefully, ideally, put on your video and unmute yourself and you can ask a question directly and we can start the discussion after that. And just one final note is please, we do ask that you use your full name as well in the Zoom chat if you do want to come forward and ask questions. And with that, I will pass straight over to Eleonora.
All right, thank you, thank you. Let me try and share my screen. Let's do this again. Okay. All right. So you should see my screen for now, and then we'll present. All good? All right, perfect. All right. Hi, everyone. I am Eleonora Alei, and I'm currently an MPP at NASA Goddard. I'm very excited today to talk to you about the two missions that I've been working on for the past few years. And both of these missions are, well, next generation missions. So that means it will, more or less, the time frame for these missions to launch will be at least at least in a decade or so. Obviously very variable these days, but this is kind of where we're looking at. So we're thinking about how the field goes in the future, and especially one of the main topics, one of the main goals for the future is to find life in the universe, or at least find habitable planets. So, but what am I talking about? Like, we're talking about exoplanets, which are planets that orbit outside a star outside our solar system. And this is a relatively recent field because actually the first discovery of a planet around a pulsar was done in 1989, but the first discovery of a planet orbiting a main sequence star was 51 Pegasi b in 1995. Very, very recent history. And that also was the reason for a reason, I think, was it 2019, 2020 Nobel Prize for Michael Mayor and Didier Queloz for this discovery. But since then, so in about roughly 30 years, we have discovered quite a few planets. And I checked yesterday that the number that we currently know of confirmed planets is 6,200 and change, so almost 6,300 actually, planets that, and equally as many candidate planets that we're still working on to confirm, I guess. And some curious things happened in the field. Like this is as you see in this plot here, we have a plot of the mass, minimum mass or mass versus the period of the planet. So that tells us how big the planet is and how close to the star it orbits, right? And you see here that these dots here are the planets of our solar system. So the purple dots, yes. So actually, well, the population that we found is dramatically different from the one that we have on our solar system. So that was very much a change in our mindset of how we think about exoplanets. Specifically, we have different populations of planets. I guess we have planets that are almost like Jupiter or even bigger than Jupiter's. We call these gas giants, and based on where they are located in around the star, in a way, we can also, we can assume that, well, we know that the period in a way is related to the temperature of the planet, right? So the closer the planet orbits to the star, the higher the temperature has, roughly speaking. And the farther it is, the cooler it goes. But obviously, when they're young planets, we still have very warm planets here, which are the planets that we actually discover here because they're young. And so they're still getting formed and they're still warm in that sense. Then we have a population of Neptune-like planets, which are, similar to Saturn, Uranus, and Neptune of our solar system in terms of mass. But again, they're orbiting much closer to the stars. This is something that's very unusual for like the solar. Like we have not thought about it before discovering these so many of these planets because we thought that the solar system was the main was, was the only data point that we had at the time. And so now with all this population of planets created a lot of discussions about how these planets are formed and how they can sustain itself. So there's a lot that we can learn about all of these planets that we currently know so far. And then there is even a population of super Earths and a random Z that I realized that I just left there. All right, fine. This population is not even there in our solar system, so this is totally uncharted territory, and there's a lot. I'm sure you have had plenty of discussions about planets in this system. But what I want you to look at specifically is that there is an overall scarcity of planets that look like our Earth. Well, definitely at the period of our Earth, but also in terms of mass. There is very little statistics that we can do here. And so why is that? Is it because there aren't any? I would argue that, and many people argue that, we're just not sensitive enough because we are biased. The reason why we found so many planets in this area, because in this region, is because they're much easier to be found because they generate larger signals. And these planets here instead generate much smaller signals. Well, we need much more powerful telescopes to be able to get to this region here. But so that leads to the question, what telescope do we need to find habitable terrestrial planets? Well, let's start with the detection phase. We need to be able to find these planets first. And how do we find planets? Well, there are two main ways. The first way, there's one that has been used for the majority of the planets that I showed, of the sample that I showed you earlier, is various indirect methods. So we have the transit method, where you basically see the planet transiting in front of the star, like an eclipse in a solar system sense. Like if you have a solar eclipse in that sense, you see something that crosses the transits over the disk of the star. Now, obviously, you don't see the disk of the star when stars are so far apart, but what you do see is a periodic reduction in luminosity of the star that you can then trace back to the presence of a planet. So every time the planet goes in front of the disk of the star, the star becomes dimmer, and you can retrace it back, and then you can find the period of the star and how big the star is. Similarly, you have measurements that relate to the wobble of the star because of the presence of a planet around the star. The star also moves. It moves around the center of mass of the system. So you can detect the movement of the star by looking at its spectrum in the case of radial velocities, or even just by looking physically at the field of the star, and the star moves slightly. In that case, that's astrometry. So in both of these cases, you see that the star is not staying in the same spot, and that's because of the presence of the planet. And obviously, the bigger the planet is, the larger the signal that it creates. And then we have direct imaging, which is a direct method because we are able then to find the light that comes from the star itself. Like in this case here, if we find a way to block the light of the star in some way that we will discuss this whole hour, basically, we can then find the light that comes from the planet. This is all well and good, but when we talk about temperate rocky planets, all of a sudden we have a much smaller signal, as I was saying. So specifically for Earth or Venus, we're looking at 0.01% of the area of the sun. So that means that the signal that the planet creates on the star is much smaller. Furthermore, if we need to look for temperate planets, so planets that are in the habitable zone, they are generally much farther away from the star. And so because of geometry, they're also less likely to transit. So for the transits, for finding transiting planets in the temperate range, so in the habitable range of the habitable zone, we are really playing the numbers game here. We need to look at so many stars, and maybe there is a chance that we find a few. This is what Plato will do shortly in a few years. Similarly, for the for the radial velocities and astrometry, we need to really look at very small variations of the wobble, I guess, of the star, because that's caused by the presence of an Earth-like planet. So most likely, extreme precision radial velocity surveys are necessary. And if you notice here, instead for when it comes to the direct imaging, we also need to be pretty accurate at really masking the star so that we don't block a lot of the area around the star, because that's exactly what an habitable planet could be. For an Earth, if we consider a star that's a 10 parsec away, the Earth is at 0.1 arc second separation. So we need to compare to the star. So we need to be able to really detect very small changes. And there is more for direct imaging. It's still very challenging. And especially, as I said, we need to have high spatial resolution because the planet is very close to the star. And as you see here, this is a simulation of how HWO could see the solar system. And you see here that in many situations, the terrestrial planets are not even visible. You need to see the planet at very specific positions around the orbit of the star. Plus, there is a problem of contrast because, as I was mentioning a little bit earlier, the the signal of the Earth specifically is much smaller compared to the signal of the star. So even if we block the light of the star, we need to be able, well, we should be able to get to differences, ratios in contrast of 10 to the minus 10. This is this number that we will find quite a lot, at least as in the requirements for HWO, for instance, or 10 to the minus 7 here in the thermal emission, because at this point in the thermal emission, so the realm of life, as we will see, the spectrum of the star is lower. So we are a little bit more it's a little bit more advantageous to look into this realm, because then you need to make less to need to have less technical, you have less technical challenge to get to these numbers. But these are still very large numbers. Like we're talking 10 billion ratio, right? So the planet is 10 billion times fainter than the star. So we need to be able to mask a signal that's incredibly large. And then we need to be able to have a stable enough observatory that allows us to still get significant signal from the planet and not meddle it with the noise, not confuse it with the noise. So we need to have very powerful telescopes. In the case of M stars, we're a little bit lower magnitudes, I guess, because we only have 10 to the minus 8 and 10 to the minus 6. But then there is the other problem, that's the spatial resolution, right? So planets orbiting M stars, a habitable zone around M stars are very close to the star. So we need to be able to really resolve very close to the star. So angularly, spatially resolve very close to the star, which is hard to do. So this is far from over. There's a lot of technical challenge that we're going through that we need to be able to solve to make these missions. All right, so this is the first item in our shopping list. We need to have a telescope that can capture the signal, and that's complicated. What next? We are not necessarily happy with just detecting the planet. We also want to characterize the planet itself. So we need to be able to figure out a way of, seeing through the atmospheres and what we can learn about the atmosphere of the planet to be able to say if it's habitable, and even better, if it's inhabited. So if there is life on it, on the planet. So generally speaking, the way we look for, molecules and relevant compounds in the atmosphere and the surface of the planet is through looking at its atmosphere. So looking through the reflected light or the emitted light of the planet itself, and then passing it through a spectrograph, and then from the getting all the light from on the spectrograph, and then the spectrograph, the grism, I guess, it's able to spread out the light of the planet into a spectrum, and then from there we can figure out what molecules are present in the atmosphere. This is something that's been done regularly with a lot of telescopes that we have so far, like JWST lately has been doing a lot of this work. So this is how we are characterizing exoplanets in this sense. And especially when it comes to habitable planets, what we want to know specifically is if there are biosignatures on the spectrum of the planet. In this case here, I'm showing the spectrum of the Earth, and here you see this is from the UV to the near IR. And this is so the albedo of the Earth as reflect. So this is the reflected light of the Earth. We specifically got this from. I'm not sure where this measurement was from, but it's either a satellite or it's even Earthshine. So we see the moon, and then we how the light of the Earth interacts with the moon, and then the moon reflects it to us, or we even look at the Earth directly with a spectrograph ourselves. But what we can see here is that there are so many features that are related to the presence of clouds and hazes. This is the radius scattering. So the fact that there is an atmosphere that scatters away some light creates this very relevant feature. Here we have the vegetation red edge and the land feature. So that means that everything that's caused by vegetation and the land, this is the kind of signatures that it produces. And overall, we see also many features of many molecules that are related to the presence of the Earth, of life on Earth, especially ozone, oxygen and ozone, right? Then we have the two other panels, which are the thermal emission of the Earth, which is caused by essentially the emission. So it's emitted by the atmosphere and the surface of the Earth, but purely by the fact that the atmosphere itself has a temperature. So all of this in this mid-infrared range, we are looking at whatever is emitted by the atmosphere itself, and we can still find a lot of features that we're also interested in, like CO2, methane, ozone again. So there is a lot that we can learn about this. And ideally, we want to have information on the context itself. So we are not just happy with detecting one single molecule, but we would like to detect at least a couple of molecules that are conducive to the presence of life, and uh, to learn as much as we can about the general context. So habitability, is there water? And that's and such as, so we want to have everything that we can. We want to gather everything that we can, because we need to understand if a molecule is there, how much of the molecule there is, and if the context can tell us if that's a real molecule or not, if it could be a false positive. All right, I wanted to briefly mention a chemical disequilibrium because that's speaking of pairs of molecules. We know that multiple molecules that are created by the presence of life on Earth are in chemical disequilibrium. They are very reactive to each other. For example, oxygen and methane, they react very fast with each other. And yet, as you've seen in the previous plot, we find both of these in the spectrum of the Earth. So that must mean that there must be some engine on the planet, which is life, that causes these two molecules to be present at the same time, because they would not be present at the same time if there was not a supply. So the analogy that I normally do here is that if you go to a cafeteria or a sushi all-you-can-eat restaurant, there is a lot of people that come in and eat food, and somehow the food court is always full of food. There's always food coming, and the only reason that happens is that because someone is constantly cooking food. So there is a constant resupply of food, and for a constant resupply of people coming in to get food. And food and people are extremely reactive. At least that's what I do at food courts. I am extremely reactive to all of these things. So there must be two systems that are, despite them being very reactive against each other, they must fuel constantly. And in the Earth's case, those are due to the presence of life. So if we find some signals of chemical disequilibrium on another planet, that will be a strong indicator of the presence of life on the planet itself. And also, we need to be able to see the spectrum of the Earth as it varied in time. Habitable planets as it varied in time. And in here, I'm showing you how the Earth has changed in time because of the presence of life. We have the first signs of life appearing around here, and then because of the presence of life, we have had a whole variation of the atmosphere of the Earth. And we need to be able to capture all of these stages of the Earth when we are looking for an exoplanet that could host life. And we should be able to point to the presence of life in all of these cases. So then the second item on the shopping list is that we need to measure a spectra. The final item is then, well, we need to be able to analyze a population. And because we should not be just observing one or two planets and then not finding, say we observe a single planet and then we find no life on that planet. Is it because we have been unlucky, or is it because there is no life in the universe? We need to be able to find a statistical sample that allows us to say that even if we have a no result, we are saying something about how the universe, the frequency of life in the universe. And this has been, I wanted to bring this one up, the Drake equation. This is not what we're talking about in terms of finding, intelligent life in the universe. But I wanted to show you that this, the measurement of, I guess, technologically advanced civilization in the Milky Way is a multiplication of a variety of factors. And I want to stress that we know more or less what the rate of star formation in the galaxy is. We know more or less what the fraction of star with planets is, but we already don't know what this is, what this number is, the number of planets per solar system that are suitable for life, and let alone everything else. So we are at this stage. We are still trying to figure out the so-called ETA Earth. There are some estimates for the ETA Earth, and only a few of these we have put here. I put here, and they're totally different. There's someone that thinks that there's no planet that looks like Earth. There's some that think that there's more than one planet per system that looks like Earth. So we have virtually no idea what the truth is. And so when it comes to planning for next generation missions, we need to be able to have a statistical sample, as I was saying, so that even if we find mostly planets that don't look like our Earth, we still can say something about the Earth, and so about the prevalence of life in the universe. And so the people that did the calculation found that the magic number is between 30 and even better, potentially 50. This number here would rule out that. So if you look at 28 planets in this case and you find none that looks like the Earth, then you can say that the ETA Earth, so the number of candidates that are Earth-like or that could be hosting life or even be habitable, is less than 10%. If you look at 50 planets, you can say that it's less than 5%. So when we plan for missions, we need to find a sample because of this reason. All right, so this is the last item on our shopping list, and so we know exactly how to make these what we want from these new space telescopes. So great, we have these requirements. What shall we build? And well, in the in the world view in the next few decades, we have a few options here that people are working on, and sorry, okay. And this has split from reflected light, so what I was telling you between the UV optical and near IR, and the thermal emission. And so for solar type stars, we have HWO. We will talk about this in a little bit. For M stars, especially, we have ELTs. Which are ground telescope, very large telescopes, so that we can have a large apertures and we can resolve planets very close to their stars. For the mid-infrared, virtually all of these two, both stellar classes could be resolved with LIFE, which is the second mission that I'm going to talk about. All right, let's start with HWO. Okay. So HWO is the new astrophysics flagship that's been in a way mandated by the last decadal, as many other before that have been mandated through decadals as well. And you can think, well, some people think that HWO is in a way a super Hubble because it's going to perform general astrophysics, and one of the astrophysics, the main goals of HWO is definitely to find habitable worlds, hence the name. But that's not only what it does. It will provide life-changing science to all realms of astrophysics, as we will see. Especially some science cases that we are looking into is some obviously planetary science, which could be done in a very thorough way with HWO, given its higher resolution that compared to its companions, I guess. Obviously, searching for signs of life. This is what we're going to talk about moving forward. But also, as I said, galaxy growth, evolution of elements, and planetary defense as well. We're talking more or less about aperture of a mirror aperture of at least 6 meters. We're probably shooting for a little higher than that, and it's going to operate in the UV, optical, and near IR space. Um, this is a very preliminary list of what we can maybe expect from HWO and what all the instruments that it might have. These are, as I said, very napkin back of the envelope measurements, but you see here that we're gonna have an aperture, so a mirror aperture, and then a coronagraph, a HRI high resolution imager that's going to perform both spectroscopy and imaging, and then a UV spectrograph. There's also a fourth instrument that still has to be defined. I want to stress that right now this is all up for discussion. This is what we are doing here in these few years, and actually the community is going to get involved in this as well. There is going to be very soon an instrument study call, so that people can propose for the fourth instrument, but also for some of the other instruments as well, to try and figure out how it is that we can build those. But if you see here, here's the magic number that I showed you before, 10 to the minus 10. This is the coronagraph. This is what's going to be used to find habitable planets. So this is what we are going to focus in. There's also going to be obviously some high resolution imager. This is case studies. These are mostly reserved to planetary science cases, but also potentially transits. So there's a lot that could be done with these two instruments for planet and exoplanet science. Very briefly, I wanted to tell you about how coronagraphy works. Well, I was saying before, when we do direct imaging, we need to figure out a way to block out the light of the system of the star to be able to see the star, the planet light, and we do so with coronagraphy using a series of masks and optical elements through the optical path. So essentially, what we do to make it super simple is we use a focal plane mask here that blocks out the light of the star. This focal plane mask creates some scattered light from the star that we also need to figure out how to block, how to cancel, and we do that with the light Leo stop in this specific very simple scenario. And this essentially gives us a region within the space that has where we have effectively canceled the light of the star. This all happens because the star is centered at the focal plane, so it's centered at the center of the image, but the planet is not, and so the planet doesn't necessarily get blocked by these optics, and so all of a sudden we can see like in this case we can see a dark hole. That's what we call a dark hole, and where we have efficiently blocked the light of the star, and we can see the light of the planet here. This is a fake planet in this case. And we can improve on this dark hole through post-processing technologies, and also through a very accurate wavefront sensing and control. So we need to really be able to model to make the rays of the star straight, so that we can effectively mask them accordingly. All right, so I was showing here the other cases that HWO does. You can find your favorite case most likely because HWO is going to do a lot of cool science. We're not going to go into more details about this for lack of time. I'm realizing I'm already taking so much time, so I need to rush up. Okay, briefly, this is what we're looking at with in terms of HWO right now. We're studying exploratory analytic cases, or EACs. You might have found this acronym around in various papers and talks. Essentially, these are the first sketches that we make of trying to analyze various technical challenges, key technology gaps, and trying to figure out how it is that we want to make HWO. And just to show you, this is similarly to what JWST was doing at the very beginning, and this is how JWST was supposed to look like, and then this is how it ended up looking like. So none of this is supposed to be final. Actually, this is used just to explore the trade space. And so far we have come out with 3 designs for HWO that then we took the main takeaways and the main pain points for each one of those, and then we are developing other designs, ESC4 and ESC5, and then the goal here is to have a single baseline for the mission concept review, which is going to happen in 2029. So this is where we're at in terms of development. If you want to get involved with HWO, you might want to reach out to your representative of the CSIT, Community Science and Instrument team. And there are a few that are specifically, well, there is a couple from ESA or European, but overall, you can reach out to any of these people and get included in some science and instrument developments. All right, now on to LIFE. That's the Large Interferometer for Exoplanets. It's a mission that has heritage from well, this is not a new idea. It's a space interferometer that has been, the concept has been used very much in the past with TPFI and Darwin. These are 2 missions that were proposed in the 70s, I want to say, 70s, 80s. No, actually, no, much later than that. So early 2000s, I want to say, at least for Darwin. And back then, we didn't know a lot about exoplanets in the first place. And so they didn't necessarily get developed as much, or at least they didn't make it to the final stage to actually being a mission themselves. But taking this heritage, it feels like now with what we know so far, we can go ahead and propose again for a space interferometer that will find habitable planets in the universe and potentially have much better luck with it, hopefully. So this is the mission reference concept of the LIFE mission. It's a space-based formation flying that is going to perform nulling interferometry in the infrared. So you see here then this image here, it has 4 collector spacecraft with a base. There are information flying, but the distance between all of these spacecrafts can change in flight. So that means that the baseline, this is here you'll find it as interferometric baseline. This is something that changes in flight. And then this formation will rotate. And I think I have an animation here. There you go. This is how it will rotate to perform some observations. And I will briefly try to explain to you how interferometry works, given the time that I have. Ooh, not a lot, but I will try. All right, so the LIFE measurement principle. So like this is the same interferometer, we're just changing the point of view. And you see here that all of these aperture telescopes and the collector telescope, you see that the aperture telescopes are all pointing to the same field of view. And if we zoom in, this is what we would see, I guess. You see a star and we know that there might be a planet there. But obviously we have some noise source, and so this is showed in a reddish hue to show that there's some noise in the simulation. And well, if we only try to think about the 2 apertures, this will be more or less of a classical interferometer. So if we have only 2 apertures looking at the same field, we inevitably have some interference patterns or fringes. And this is caused because the light rays coming from the 2 apertures are interacting and interfering positively and negatively, constructively and destructively, and we are able then to magnify the flux that comes through the red bands in this image and cancel out the black bands, everything that's in these black bands. But so in this case, we're seeing that we're magnifying the light of the star and we're blocking the planet, so we don't like that. We want to have a phase shift, and we can do that by adding optics to the system, and then all of a sudden we are blocking the light of the star and we are multiplying the light of the planet. We are increasing the light of the planet. And this is exactly what we want. Similarly, if we have 4 more complicated optical scenario, but the gist of it is the same. We will create a more complicated fringe pattern, but still we will be able to mask out the light of the star and then have the planet move through through regions of constructive and destructive interference so that we can trace back where the planet is and how massive it is, and then get the flux of the planet itself. And so the fact that we move the formation of line, the array, that allows us to change how the planet is positioned against the interference pattern. And I have it here. So if we start rotating the planet, the planet goes between phases of being constructively interfered and destructively interfered, and it creates this light curve here. And from this, we can then derive where the planet is and how bright the planet is. And this is interference 101, as I understand it myself. If you have more questions, I know who to point to for more complicated answers to these questions. All right, the life science program is more tailored towards terrestrial planets, so it's not going to do other science like HWO is, but it's definitely going to observe, again, 30 to 50 planets around sun-like stars. This is, again, because we need that magic number to be able to rule out to have some information on how the universe is formed, and then focusing again on Earth-like biospheres, non-Earth-like biospheres, and then potentially technological signatures as well. Notably, it's also going to look at M-star planets, and which is, as I said, something that HWO cannot do because those planets are very close to the star, but that ELT can do, for instance. Yes, I added this slide last night. If you want to get involved with life, for now, just send me an email and I can send you all the details on how to get involved. I'm also one of the life science community leads, so I can just drag you into our meetings. And if you want to contribute to the science community, please let me know. All right, finally, last bit, the synergies. This is what I've been working on in the past few years, and why I work on both missions and why I think we should support both of these missions. Well, as I was saying, we have similar discovery space between HWO and LIFE, and you see here some simulations that were done to estimate how many planets of each kind HWO and LIFE will find. And especially here, again, 28 or 27 plus minus 5. You see, again, this number again and again. And the reason for that, as I said, is to have a statistically significant sample. So there is definitely an overlap between what HWO and LIFE could find. Specifically, also when it comes to spectral type stars, as I was saying, HWO is not really going to do a lot of M stars, it's still going to do quite a few, but LIFE is definitely going to hammer down on M stars specifically because it's easier for an interferometer that can change the baseline to virtually make the fringe patterns as wide or as small as you want, to be able to block out exactly the amount of angular separation that you need to block out the star, but not block out anything else. This is something that you cannot easily do with a coronagraph because you have a physical mask, or you have a physical space that you cannot go over, which is called the inner working angle, which doesn't allow necessarily very, very close in planets to be observed. These are known planets within 20 parsec that could be detectable with LIFE and HWO. And so you see here that there is some overlap in this region here for both, but otherwise they're somewhat complementary in a sense. So we could cover the whole space of known planets for the most part, or many of the known planets, with these two missions. So in case we want to characterize them even better, we could do that. And these are for instance, the currently known planets that could be observable by both HWO and LIFE. This is granted a 3-year-old paper, so there might be more. There would be more. But if LIFE and HWO were to launch tomorrow, we could already start seeing some the same planets with the two different instruments. And this is important. When it comes to the characterization, bring back to this picture that I showed you before, HWO and LIFE will uncover different windows, different areas of the different regions of the spectral flux of the planet itself, especially when it comes to the Earth. Earth-like planets, HWO will cover the reflected light of the spectrum, and LIFE will cover the emission part of the spectrum. And so as you see here, access to different molecules, different features, different perspectives on the atmosphere of the planet. So that's why we want to have more of them. And finally, this is what, to hone in on this, I worked on it in a paper a couple of years ago where I started simulating observations with HWO and LIFE separately, and what is the added benefit of having HWO and LIFE together. The way I did it is through atmospheric retrievals. This is something that's a technique that's used to model to understand how data relates to the model, how data fits to a model. This has been used for JWST very recently. And so by looking at the spectrum of the planet and fitting a model to it, you can have information on all of the parameters of the atmosphere that you're interested in. You can do this also for missions that don't exist, if you are able to simulate how an observation could look like. So if you have a good noise simulator for the spectrum of each planet, of a planet with life and HWO, then you can do this. And very quickly, going through the results, you see that you can see already the different purview, that the different areas that HWO and LIFE are covering, and what is the added benefit of having both. So HWO is not going to do a very good job in determining the atmosphere of the temperature of the atmosphere. You see here, this is the pressure versus the temperature. And well, this is fine because in the reflected portion of the spectrum, there is not a lot that you can glean about the temperature of each layer of the atmosphere. That's not what that region of the spectrum is about. But on the other hand, if you have access to the thermal emission of the planet, this is exactly what you're measuring. So all of a sudden, LIFE is going to be able to look at all of these, probe all the layers of the atmosphere and have a much more accurate estimate of its temperature. So if you have both, all of a sudden, you can get a very sharp constraint on the temperature and on the pressure at the surface of the planet, which is huge if you want to look for habitability and if planets are habitable or not. Finally, when it comes to the chemistry, you can see that because of the fact that they have access to different areas, the results will also be different. If I look for HWO by itself, I can constrain N2 and O2, the bulk elements of the bulk molecules that compose the Earth's atmosphere. You can also constrain water, and you can constrain to some extent methane and ozone, but only if you have UV coverage, which is technically challenging so far. When it comes to LIFE, you have no idea what the atmosphere might be made of. You can have you can infer based on the weight of the atmosphere, but no real measurement of N2 and O2 in this case. But you have CO2. You have a much easier time getting ozone, and you can also get a methane as well, a higher resolution especially. All of a sudden, if you do both together, there you go. You have the whole picture of the atmosphere. You can have surface biosignatures. You can have methane. You can have CO2 and O3 that you get for LIFE. Maybe you could argue that maybe HWO would not need to put in the effort of having a UV coverage if there is LIFE online. So you can start making all of these trades that go beyond the single mission, and then all of a sudden making trades that cover many missions at the same time. So yeah, somehow I managed to kind of get a good time. And so yeah, I will leave you with some conclusions. Exoplanets are a new but very active field, and the next task is to find habitable terrestrial planets, but we need new instruments. Luckily, HWO and LIFE are coming in to save us from impending doom, and we will, if we have both of them, we will be able to have a full picture to find life in the universe. And so with this, I'm done. However, I can, since this is a discussion, I wanted to leave some discussion points in case we want to start talking about these. And some questions that I have in my research and something that you might be interested in is, well, we discussed very briefly about HWO and LIFE and how they synergize, but obviously there are other new generation instruments. For instance, I'm thinking about PCS or other ones that might be online around the same time. What can we do with that? Or another question could be, what can we do now or soon with current or short-term missions to improve on next generation missions? How can we optimize, for instance, with precursor science programs, EPRVs, Plato, and missions like that? And then again, yeah, what would you want to see and explore with the new missions yourself and with your science? Because as I said, this is all very much just starting to get built. So we still have a relatively high leverage as a community to decide how these missions should look like. And with that, I'm done.
Ooh, thanks so much, Eleonora. That was a really, really great talk. Really interesting stuff. We're now opening the floor to questions or discussion points that anyone wants to make. If you'd like to ask a question or make a comment, please do just raise your hand and I'll call you forward. And then, if possible, please do unmute and put the camera on to ask your question. If you absolutely cannot do that, then you could also put some questions in the chat if you want to as well. So I guess while we wait for the first couple of questions to come through, I did have one quick one, which might be
Yep.
an easy yes, no. You talked about how HWO has other science goals, like in astrophysics and for solar system science. Is there any
Mhm.
scope within life for it to be used, for example, for outer solar system bodies or anything like that? Or is it purely exoplanet focused?
So, again, this is not set in stone, so grain of salt here. But there might be, like, I feel life was definitely tailored to be more exoplanet based. One other science case that could play a role into this would be the study of disks, but still exoplanetary disks. In terms of solar system science, I'm not sure because I mean, we could think about it because I guess what you could do for solar system science with an interferometer, I guess the main issue here is that the interferometer is a nulling interferometer. It's not a regular interferometer, I guess. Um, but you could maybe, if you're interested, fine grain some very specific regions of some solar system bodies, that something that you maybe cannot do with like a probe or sending a spacecraft there and take pictures there, because. But I don't know how much you can really do. I don't know. Like so far as far as I know, there's not been a huge discussion on this in the life science community and program. There might be some interesting cases that we haven't thought about. So if you have any ideas on your end, we can chat. But I don't know. I'm trying to think, and it doesn't necessarily come to mind like obvious solar system cases for life.
Okay, thanks. And I guess Angeli's hand went up first. So do you want to ask your question?
Yeah, thanks. Thanks for the amazing talk, Eleonora. You mentioned a lot of the synergies in terms of determining the temperature profile and the chemistry. I was wondering if you've looked into how cloud and haze properties could also be jointly constrained by these like different wavelength regimes as well.
So not in this paper. In this paper, I didn't take into account clouds at all. So this is a very simplified Earth-like case. Everything is set to like a constant profile. Nothing looks exactly like the Earth. This was more of a proof of concept that I want to bring back with a follow-up study. And yes, definitely at that point, I would expect to include clouds. From our other studies that we have done in the life team, the the clouds have been studies, and it seems like more in the Earth, well, real Earth data and Venus-like data, and it seems like there's not the the thermal emission doesn't necessarily um, feel the clouds too much, which could be a good thing to then disentangle the visible part. Because if albedo and radius is a very degenerate problem. If you can get the radius from life or some other measurement, could be EPRB, for instance, all of a sudden you can disentangle that, and then you can understand what the clouds look like. So I haven't done it. My gut feeling tells me that it could be cool to look into it, and that could be very very relevant result. But I haven't done it, so I cannot I cannot confirm nor deny.
Sounds exciting. Thanks.
Yeah.
Okay, so Rob put a question in the chat. Rob, if you're online, do you want to just ask it in person?
Sure. So Eleonora, just a quick question on your HabWorlds simulations. What wavelength range, spectral resolution, and mirror size did you assume? And then I have a follow-on question from that.
Okay, so on this one, I don't remember. This was this was 2 years ago, 2 years ago, and I started working on it 3 years ago. This is definitely old school, and I was not even using the new exposure time calculator that since then I developed. So I used between 0.2 and 2, as you see here, and I think it was basically was a LUVOIR, but I think it was a 6 meter LUVOIR. So everything that looked like LUVOIR, but then just changing the LUVOIR be set up, but then putting it onto 6 meters. So all of this could also change, with the new ESEs.
Got it. And then you very nicely showed how HWO and LIFE are very complementary to each other. You probably
Yeah.
said this and I completely missed it, but will there be an opportunity to observe the same target with both of the spacecraft? And if so, what would that target look like? Like what type of planet would it be? What type of host star would it be?
Okay, so yeah, the closest thing that I have to it is this one. These are currently known planets that both HWO and LIFE can detect together. Obviously, since we don't know many Earth-like planets, I cannot confirm an existing target with the in the Earth regime, but life. And if you think about the modern Earth at 10 parsec distance, that could definitely be achievable by both HWO and life together. And virtually all of the close-in planets life could get. So that's an easier time in that sense. Probably is HWO more the bottleneck as to how close you can get to the star. So right now, these are what we can do if we were to launch tomorrow. But these missions are both built for terrestrial planets, and so I would assume that terrestrial planets around sun-like stars, those are achievable by both missions.
Excellent. Thank you so much.
Yeah.
All right, any other questions? Yeah. William, go ahead.
Yeah, I guess kind of following on Rob's question, I was curious if you kind of anticipate, right? So these both these missions will be pretty like kind of target limited, I guess. Like they'll only have to pick a few. Do you think like being observable by both will be like something that's taken into consideration, or maybe if one ends up launching before the other, do you think that'll be something that will be considered when you're picking targets for each of those kinds of synergies?
Well, selfishly speaking, I think so. Until I'm involved in these missions, I will die on this hill. So surely, there's definitely considerations about what can be done with if one is launched before the other one, because both of these missions so far, and probably rightfully so, are assuming to be self-consistent, right? So they're going to find planets and then they're going to characterize planets. But if one of the other missions, especially in the case where they're not synchronous, right? If one of the two missions is online before the other one, then that could point to like prime targets to follow up directly with. So you would skip on those targets, you would skip the detection phase, right? Or the detection phase. So definitely this is something that we keep in mind. And in both of these missions databases for looking at stars and planets, there is special consideration for planets that have been known to be to host stars that have been known to host planets. And potentially I can see how planets that have already been discovered that could be interesting to be looked at with both of these missions to be prioritized. So right now, as I said, it's very preliminary, so we don't necessarily know how the scheduling is going to go, but it will line up in time. And I'm sure that this will be definitely something to follow on. Oh, I hope so, I guess. Yeah.
Thanks. So just to run off that question, so if you were to observe a planet or plan to observe a planet with both instruments, how important would it be to be observing them like at the same point in time? Like if there was some kind of temporal difference that may, thinking about kinetics in the atmosphere or things that may change. So how can you make sure that you are getting, or how important is it to observe them very close together in time, or could you come back a few years later and then if the spectra don't seem to disagree, would that be explainable with the models we have or not?
In principle, planets vary on the daily, right? And when we are observing these with these missions, we're still integrating over multiple days. So we're already getting a smeared signal of an average of whatever the planet has done during the observation. Definitely, especially in the case of HWO, phase is incredibly important, right? Because it changes the amount of light that's reflected. So in an ideal world, you would observe them at the same time, but also for these for the missions to work separately, you need to observe them multiple times to detect the planet, right? So I think that between now and 10 years from now, we need to find a way to model the phase variations accurately enough that we can be happy with observing it at different times. Also because independently of the fact that we have both missions operating or not, because even for a single mission you want to confirm a planet, you need to determine the orbit, you need to detect it 3 times at least. That's what we think, right? So already by virtue of having time pass, the planet has changed. So we need to be able to figure out a way to have it not matter as much, or to at least predict when we want to observe it so that the phase is about the same, but it cannot be exactly the same time. And to do this, we want to be able to probably model the phase more accurately, at least have an idea of where the orbit goes. And so all of this study of how orbit modeling goes compared to detection times is a whole other realm that's related to optimization of the scheduling of the mission, which is super complicated, and we're also looking on it. When it comes to life, though, the phase doesn't necessarily matter, right? So as long as you don't have a tidally locked planet, which has very warm side and very cold side, if you're looking for a temperate planet, it's going to be temperate overall. Doesn't matter where it is for a normal enough orbit, right? But for HWO, definitely the phase is important, and so we need to figure out how to model those, and then maybe we can also put in the what if we're observing with another mission at a different time. Very much, very cool question. Very very interesting to look into this, and we will in the fullness of time for sure. Yeah.
All right, thank you. Any last questions? No, doesn't look like it. Okay, so with that,
Okay.
last thing to do is just thanks so much, Eleonora, for your great
Okay.
talk and the great discussion afterwards. Just to add a quick announcement for the next Rocky Worlds discussions, we're going to be off schedule slightly. We're going to be 1 week later into July, as to not clash with Exoplanet 6 and EAS. And our speaker is going to be Cayman Unterborn on July 9th, same time as usual. And